Hello, good afternoon. I know I'm between you and your lunch, so I'll try to keep this short. But so today, I'll be going through an overview of Bumblebee software architecture. So hopefully you can take a look at some of the things that we do and get some inspiration for your own software architecture, for your own AUVs. Of course, some of the decisions that we have made haven't been the best, so don't just copy everything wholesale. But yeah, hopefully you can find some inspiration based on what we do. So first off, who are we? So we are a fully undergraduate underwater robotics team from NUS. We have been founded in 2012, and currently we have about 30 members from various faculties at NUS, like mechanical engineering, electrical engineering, computer engineering, and computer science. So that this is our current team, and our motto is to engineer autonomous systems of the future. Yeah. So these are our three vehicles right now. So at the center is our AUV, which you can see over here. It has been redesigned over the last 3 years during COVID, and we just went for its first competition early in August. And it is engineered to be a competition-focused vehicle, and we reduce the size and weight while maintaining the same capabilities as the previous generation. And then on the left and right, you can see our newest vehicles that we are taking to a competition in November in Australia. So on the right is our surface vessel, built on the WAM-V platform, and it has multiple onboard sensors for navigation and localization. And it also integrates with the drone on the left, as you can see. So this year, the newest thing at the RoboX competition in Australia is integration of a drone. So we don't really have a lot of experience with drones, but so we're trying to customize an M210 drone and try to make it capable of autonomous navigation and also takeoff and landing as part of the competition. Yeah, so these are our three vehicles. So now I'll talk a bit more about our software architecture. So before that, so some of the achievements we have over the past few years. Most recently, we won first place at RoboSub at the University of Maryland in Washington, D.C. Yeah. Yeah. So now I'll talk a bit more about our software architecture. Thank you. Yeah. So now I'll go over our software architecture a bit. So as I'm sure most of you here we use ROS as well. ROS Melodic on Ubuntu 18.04. And most of our code base is in C++ with some Python, usually for the ML. So this is a brief overview of our software architecture. So we have three main sections. We have the perception section, where we combine machine learning object detections and sonar images in our vision pipeline to localize and identify objects. So this might be like the tasks in your SAUVC. And then we also have a navigation, where we take our different sensors and we fuse them to get localization for our vehicle. And then we output to controls, which controls the vehicle using thrusters. And finally, to tie everything together, we have a mission planner. So today I'll be talking more about the perception part and the mission planning part. Yeah. So first of all, let's talk about machine learning. So in the past, we heavily rely on traditional CV methods. But as I'm sure some of you might have found out, it's very hard to tune, and it can also be very challenging in different lighting environments. So maybe when it's cloudy, you have a set of values. And then when it's sunny, you have a different set of values. It can be very challenging to switch, especially during competition when pressure is high. So recently, over the past few years, we've moved towards more machine learning-based object detection. So currently, we're using PyTorch and YOLO v5. So as you can see on the right, it works quite well. So on the top right is our machine learning working on our RoboSub obstacles. Yeah, so we chose YOLO v5 because it had a high inference speed and was very accurate. And also it easily allows us to train custom data sets as well. And the last thing it allows us to do is to export to the TensorRT. So TensorRT is this library for Jetson devices. So we have a Jetson Xavier on our AUV, and we use the TensorRT library to further optimize inference speed. So on our AUV, we can get anywhere from 12 to 15 frames per second for machine learning, which is good enough for what we need. And of course, your machine learning is only as good as your annotations, right? So we found that it's very important to have a good annotation pipeline. So what we are using is LOS, which is an open source web annotation tool. So one of the most important things that we found is that we need to be able to have multiple users be able to annotate the same set of images at the same time, right? Because especially during competition, you'll be taking a lot of bags, you have a lot of images. You want everyone to be able to annotate the same set of images. You don't want to have to manage people to have to delegate batches of images to different people. So what LOS allows you to do is it allows you to set up different tasks, a different set of images that you can just let everyone annotate. So you just have to set up the different pipelines, and anyone with an account can just log in and just annotate whenever they're free. So this has worked out well for us. And it also has a review pipeline where you can review the annotations before exporting, because some of your teammates may draw some slightly dubious boxes, like you see in the bottom right, which might affect your ML. So reviewing is also very important. So it also has a review process. So this is the open source tool that we use. And then lastly, the new thing that we tried this year, which is very interesting, is that, so traditionally, I know some teams are using a sonar on their vehicle to localize objects, so to tell how far they are and what orientation they are. And in the past, that's also what we did. But we found that for shallower waters, like in pools, sonar images can get very noisy, whether it's because of the reflection of the pool walls or of the top of the surface of the water. And this year at RoboSub, the competition venue changed from about a 50-meter deep basin to indoor Olympic swimming pool. So this was a very big problem that we have. So at every pool test, we would spend a long time just tuning our sonar parameters to try to get a clean image. So on the top right, you can see we're trying to detect a buoy in the water, and you can see from the sonar image that it's quite impossible to tell which one it is, because there's a lot of noise and there's also a lot of false positives, a lot of echoes. So this year, what we've tried to do is we have tried to use machine learning to help with object localization as well. So we are making use of the superglue. So what superglue is a neural network, and it's able to perform matchings on two sets of images to give you the features. So you can see a bit of a demonstration on the bottom right, taken from the GitHub page. So what you don't need to train, there's nothing to train. What you do is you supply an image, and what superglue will do is you will match this image to, in our case, the camera feed, and they will give you a set of matchings between that image, the target image, and the camera feed. And then once we get these matchings, we can use homography to estimate the distance and the orientation of our obstacle. And so this has really helped us to be able to accurately figure out the rough distance, as well as, more importantly, the orientation of the obstacle in the water, so that we can align to it. So this is something you can try out. It's very cheap to get started. You just need one camera and just a bit of machine learning. It works on CPU as well. We tried it on CPU, and it works fine. So this is something you can try out. And then now I'll talk a bit more about our vision pipeline. So for our vision pipeline, we fuse our sonar when it works with our machine learning or traditional CV object detections. So what we do is we filter sonar images to get regions of interest, and we use simple heuristics like the boundary box size and also the shape of these detections. And then after we get these regions of interest from the sonar images, we fuse them with our machine learning object detections or traditional CV object detections. So what we do is we calculate the image coordinate. So we use a camera matrix, and we take the sonar image and we find the range and azimuth of the object, and then we project it onto our camera feed so that we can match it with our object detections bounding boxes. And then after that, we use a particle filter to track the 3D position of these identified objects. And we use, of course, several heuristics to reject these detections based on maybe bounding box size, or maybe even if your vehicle is moving to the left and then your bounding box will move to the right. So we use several simple heuristics to reject matches. So that's our vision pipeline. And so I think the most interesting thing that we tried this year is our new mission planner. So traditionally, I'm sure most of you are using a finite state machine-based mission planner because it's very easy to implement, and there's a lot of resources out there to teach you how to use it. But we found that finite state machine-based mission planners have several disadvantages. So you see on the top right, modifying states in traditional finite state machine-based mission planners can be error-prone because there's a lot of different states and a lot of different state transitions between these states. So if you have, for example, you have n states, you will have n squared transitions. So if on the top right you see if you have maybe 7 different states and you want your vehicle to be able to transition between any of these 7 states, you end up having 7 squared, so 49 different transitions between your states. So we found that editing the mission plans is very fragile, and when you remove one state, you end up having to check all your transitions to make sure that you haven't missed out anything. So this year, what we've done is we moved to a behavior tree-based mission planner. And so we can easily configure robot behaviors by adding a repositioning node. So what we are using, if you are basing our mission planner on a batteries included C++ mission behavior tree libraries, it's called behaviortree.cpp. So using this library, we're able to accommodate many different scenarios and many different failure states, and this makes our mission plans very robust. And there's also a very high level of composability and abstraction. So for these mission trees, we can reuse the nodes and the subtrees at different parts of the trees, and we can easily reuse the same behaviors over and over again. So maybe in our competition, we have a subtree that deals with centering the object into the center of the camera feed, and then we can easily reuse this subtree wherever we need to in our mission tree. Yeah, so maybe some of you are not very familiar with behavior trees, so I can give a short introduction. So let's say, for example, you want to program an AI to play Pac-Man, right? So maybe your first goal is to have a very greedy AI that just eats pills, right? But you also, of course, you want to avoid the ghosts. So what you want to do, so how you read this mission tree is the question mark is a fallback node. So what a fallback node does is, if you do the first thing, the left side, and it fails, then you try the right side. If you do the left side and it succeeds, then you just cycle the tree again. So what you do is you check the left side, and you check if the ghost is closed. And if the ghost is closed, then the arrow means a sequence, so you do the next thing in the sequence, and then you avoid the ghost. So you'll keep doing that until the ghost close becomes false, and then you move over to the eat pill, so you fall back to the next node. And then let's say now you want to introduce even more advanced behavior. Let's say after you eat a power up, the ghost may be scared of you and you want to avoid the ghost. So all you have to do is replace the bottom node there with another subtree. So this is actually quite similar to the previous tree. So what you do is you check whether the ghost is closed. If the ghost is closed, you go to the next thing in the sequence, and you check if the ghost is scared. If the ghost is scared, you chase the ghost, and then you repeat the tree again. And then the moment the ghost is not scared, you will fall back to avoid ghosts, right? And then if the ghost is not closed, you'll fall back to eat pills. So using many of these different subtrees and many different nodes, we're able to compose all these subtrees to create very advanced behaviors for our robot. So if it loads. Yeah, so here are just some videos of our robot, our AV at RoboSub, and all this is powered by a behavior tree mission planner. So on the left, you can see we're trying to bump into the batch boy. On the bottom left, you can see us try to shoot a torpedo through the small hole on the bottom left. And on the top right is we are trying to pick up a lid and drop balls into the bin, and on the bottom right, we're trying to pick up several bottles. Yeah, so all these behaviors are powered by our behavior tree mission planner, and being able to reuse the same mission trees, the same nodes, and same subtrees allows us to create very complex AI, very complex mission plans that can account for many different states of the mission. Yeah. So actually that is all. One sec. Yeah. So thank you very much. If you have any questions. If you have any questions about software architecture, you can ask me, or you can check out our Facebook or Instagram page, as well as our website to find out more about our vehicles.